Yeah.
Do you think your model can help us understand, like, within individual variability in terms of behavioral?
Yes, yes, yes. So not in this particular version, but the version I'll show you at the end, my colleagues who developed the visual component of the model that I'll show you actually have used it to capture individual differences in very young children in terms of visual exploration, right? So running huge batches of simulations and running then around a parameter value that captures some set of data, running a distribution of values around that, and then being able to map that on. That changes, can have big changes in the way the model performs, especially if you run it in kind of longitudinal cases. And so then you can kind of map some of that onto different patterns that you see in children, right? And if you find that that manipulation is a parameter that's specifically related to neural encoding of working memories, for instance, then you can make predictions that perhaps if you have differences in children in their working memory, it could translate into how they're doing in that task. And that's we have a couple of those predictions in the new grant, right? So yeah, I think there are definitely ways. That's the one way that we've started to kind of look into that. We could look at the variable responding in the model and other ways to do that. There's also, right, I mean, pushing around the specifics of the parameters, right, and testing how far, you know, it gets tricky in some of these dynamic models, right? If you push this parameter very far, it can totally change the regime in terms of the number of peaks it can sustain and what kind of attractor state it gets into. And so, you know, you want to make sure you're still not pushing it so far that it can't even, it's not a model of this anymore because it's not doing this task anymore. But there are definitely ways to kind of push that around. Yeah?
For what you've shown us so far, what does the model teach us beyond the experiments?
Yeah. Well, for me, the big thing with the model is, you know, I felt like the experiment suggested that the spatial component was important, right? And there's other lines of work that we know, you know, either from neural work, right? And we know how the dorsal and ventral streams work in terms of encoding aspects of the visual environment. And we know from other studies by Richardson and others that we encode information about space. So this makes a lot of sense, right? For me, the model being able to kind of lay that down in a way that forces me to be concrete about the way that information is getting passed across the systems was kind of important to see how that binding works, right? And I've constructed the model in a way that I you know, embodied the hypothesis I was interested in, but there was still a lot in terms of there's a lot of things this model can't actually do, especially with the dynamic nature of the parameters. It's possible to get it into states where, for instance, it won't do the selection task because the memories for where this object had been could be so strong that it can't move it over to be able to pick this object in a new location, right? So you can start to then pull apart some of that balance between, you know, being too bound to where this is to what they can actually do, where they can generalize and things.
Yes, the benefit is in not just the mapping of how important these cues are, but the process under which.
Yes,
So
exactly.
does the model make predictions about
Yes,
the process?
yes, and I'm going to get to that at the end. In terms of pushing that forward. I mean, it did make this kind of prediction that this shouldn't work, right? And this kind of confirmed it. That one was kind of not as detailed as what we'll kind of get into, okay? Okay, so the model captures that one again. Summary so far. The child data and the simulations in these experiments demonstrate that the child's behavior in this task is not about hidden objects or complex inference process, I don't think. It's about associations between objects and locations, such that if you make the association between an object and a location weaker, it's going to disrupt the linking of a name to that object. And a prior association of an object and location disrupts linking via temporal congruence. So I think space is special for facilitating binding. And I'm going to try to speed up a little bit because I want to make sure I get through some of the other stuff. The next question, whether these spatially grounded processes could be seen out there in a more kind of general situation. Not going to go all the way out to the home, but you know, I had some idea that space might be something that children are using more generally, because my son actually used space to refer. So here he is at 18 months picking up a banana, which was the favorite food at this particular meal. He finished off all his bananas pretty quickly, and then he would actually point to the empty location in space to tell me what he wanted more of. Okay? I was like, oh, you're using space, right? So what to test this was bring parents and children into the laboratory. We went a little bit younger, just so we can get more variability in terms of naming performance. We had them the parents teach their children names for objects. Of course, we told them nothing about what we were actually up to. It was just kind of freely playing and naming. Coded the spatial position of the objects as the parents taught the words, and then the experimenter, to keep everything fair, tested children's learning of the names. Our question then is whether parents actually tend to keep things separate in space as a cue, as a guide, as a help for their children, and if they do, does it matter for what children do? So this is just a quick time slice. I'm going to try to go a little more quickly here. What we see is we're coding in terms of the right hand and the right table of the parent and the left hand in the left table over time. These little hash marks are when mom named it. And as you can see, this particular mom tended to keep things pretty well spatially segregated. She's got the binoculars on one side and the spring on the other, and she kind of keeps it that way all the way through. Okay? Not all moms did that to the same extent. So this mom starts with the objects on one side of the table. They actually both do. We put them there. Okay? And then she kind of has one object over there, but then she switches them all. So she starts with them all on the right side of the table, and then she switches them all to the left side of the table. Okay? So parents varied. We coded a number of different things, just to give you a sense. We coded the two hands, so how often did they keep them in their hands? They did it from a third of the time to all the time. And then we coded, even if it wasn't in their hand, how much did they consistently use space, so keep it on the same sides of the table. That was from about half the time to 86% of the time. And interestingly, this one mattered. So this correlated with children's learning. So this is the percent of time the mom or parent kept objects in this consistent spatial position. And this is child's correct choices. And as you can see, there was a high correlation between how consistent mom was and how well children did in learning those words. Okay? Interestingly, it wasn't correlated with their age in terms of the specific number of days, the number of times mom named, or the total time holding. And for me, this was a big constraint. It's not consistent with the child's handling. Okay, so it's about what mom's doing with it, not about what baby's doing, which is kind of interesting. Okay, so words occur in time, and the reference occur in time, and the reference occur in time and space. I think space helps us to organize our behavior in many ways, including where you're looking and what's selected, right? In these tasks, you're behaving, you're looking at something, you're picking something up. Okay? We know, as I said, we encode spatial information in memory for these, and you can think about this. If you read a novel and there's a character introduced, and then 5 pages later you've got to remember where that character was from. Sometimes you can't remember that bit of information, but you can remember where on the page that character was introduced, right? We keep this information around. I think space can then activate those memories, and this can enable the binding of words to objects and allows things in the just previous past to be kind of brought into the present to bear on what you're doing. So in this way, space serves as a binding agent for novel word-object mappings, and the shared space, right, the fact that when we interact with each other, we do so in a shared space that's consistent, can be used, I think, to help ground our understanding of children's use of these kind of social cues. Okay. So in this, what I've shown is the current behavior is a product of both represented knowledge and the specifics of the current task. There were interacting systems of memory, attention, and action here. And we're looking at how this interaction folds over development. In that next part, I also want to kind of look at this and think about more about time scales and change over time, looking at retention of name-object mappings formed in ambiguous naming situations. So I'm going to switch the task here. We're going to use a reference selection, also sometimes called a fast mapping task. In this task, what you do is give the child some stimuli that you probably checked with mom that they know the names of. Novel, give them a novel name, and when you do that, children, 24-month-olds, will pick this object as the referent of the novel name. In the literature, there are a couple different ways that we think that they do this. One is by what's called a mutual exclusivity bias. That's the idea that because they already know duck, shoe, and block, they just assume that new word Zeb has to go with the novel object. Okay, so that's using represented lexical knowledge. Another possibility, however, is that they're doing it just based on the sheer novelty of this cool thing. So the novel name, nameless category principle suggests that novel names go with things that are not yet named. Or it could just be, this is really all you attend to because it's the most novel salient thing there. Okay? It just grabs all your attention. Okay, the way we do it in the lab, a series of warm-up trials. So we present them with 3 objects that we've checked with mom, they know the name, and have them get each of them in turn, scramble them around in position. Then we do these reference selection trials. So here they're going to have 2 familiar objects and then a novel object. Sometimes we ask for a familiar, but sometimes we ask for a novel. And then we have these, and they kind of go back and forth. We take a 5-minute break, and then we do a retention where we put all the novel objects together and ask them to get each by name. Okay, so we're pitting each of the novel names they made a mapping for against each other. My student Jessica Horst and I showed in 2008 that even though 24-month-olds are very good at selecting the dog when you ask, selecting the yak when you ask, after a 5-minute break they show chance level performance, right? So they're not maintaining those over a delay. We actually also did an extension to a new category member, but you don't extend what you never kind of got in the first place. Okay. Recently, Sarah Cucker, who just finished her dissertation a couple years ago, examined these processes in children who are earlier in vocabulary development. So she replicated with 18-month-old children. And what she found, I think, was quite interesting and started a kind of line of work. So what she found was, in terms of percent correct, on those warm-up trials, these children were excellent, right? And we're asking for things that we verified with mom. Do they know what this is? And actually, would they use the word dog or would they use puppy? So we're even using the right words. They do great. They do great on the novel one, getting that yak. But when you ask them to get the dog in the context of the yak, they fall to chance levels. And that is, of course, because they are selecting the novel object. Okay? They can't get the dog when that cool yak is sitting there. Okay? Now, as I said, parents verified that their children's knowledge of the familiar names, and the children selected the familiar names with high accuracy when asked on warm-up trials, okay, for 94% better or better across children, okay? So it's not likely a failure of a lack of knowledge, but I think it's really that the novelty bias at this age is so strong that it's beating out their word-object mappings, okay? This contrasts in an interesting way with the data from Horst and Samuelson and suggests there's this dynamic interaction between novelty and knowledge between 18 and 24 months of age. Okay? You also see in some work by Emily Mather and Kim Plunkett, some very interesting work using preferential looking kind of tasks where they introduce words. Also some of these interesting changes in novelty. You also can see it. I also think this data is interesting in light of some other work that we did where it turns out that 18 and 24-month-old children will show the same kind of response to novelty. So in this case, what we're doing is we do a reference selection and retention task with all novel objects. Okay? And we're going to manipulate the novelty of some of those objects by pre-familiarizing them. Okay? We don't name them when they're exploring the objects. And like I said, we do this with 18 and 24-month-old children. So this is what it looks like. It's the same kind of task in some ways. I'll show you where it's different. But we familiarize them. And we just give them the objects to play with. We do make sure that they play with all of them a little bit so they're familiarized. We do the same warm-up. Now what we have are these all-novel trials where some of those objects were things that they just explored up here, but others were not. Okay? And we do all known ones just to kind of keep them going. Okay? And then we do a break and we look at mappings of multiple kinds actually. This is what we found for 18 in purple and 24 in blue. They're very good at that warm-up. They do good on those all knowns. Again, this is in the context of only knowns, so that's not the problem we had with 18-month-olds in the last study. And they do well on those novel. And what they're doing here is selecting the most novel object in that case, okay? What we would call the super novel, the one that they didn't get to see before, okay? But when they do that, so they get the yak as the most super novel, they don't show retention of it over a delay. So here, novelty is acting in a similar way for these children. In a context where the objects only differ in novelty, 18 and 24-month-old children are similar. Okay? I think together these data reveal a dynamic interaction between attraction to novelty and represented knowledge over development. We see evidence of similar interactions in 12 to 14-month-olds in a cross-situational word learning task. And we actually see that this interaction is continuing to shift through at least 30 months of age and even later, I'm sure. In that 30-month-old children not only reliably select the known objects like 24-month-olds, but they also retain those mappings over a delay. Okay? Now, interestingly, we can get 24-month-olds, like, as I've shown you, to perform 18-month-olds. I think that suggests there's some continuity. There's actually other data that suggests that we can make 24-month-olds act like 30-month-olds, which also supports that idea of continuity. If we manipulate this task, we can get a whole range of different behaviors. So this is a prior study that Sarah had done. We did the standard reference selection and retention task, but we gave them 2 minutes of pre-familiarization. Same pre-familiarization with the novel objects, no naming. These were 24-month-olds. So they just get to explore these objects, and then we do our task. And here, these are the Horst and Samuelson data versus Sarah's pre-familiarization data. And what you can see is they do great on the warm-up, the known, and the novel reference selection. And if they've got pre-familiarized, they retain those mappings over that delay. So just a little bit of prior exposure and familiarity with that object helps those children form a mapping that's now strong enough to withstand that delay and act like a 30-month-old. Okay? 18-month-olds in another series don't do that. Okay? So 18-month-olds still show us their bias to the most novel thing. They still do fine on those novel reference selection trials, but they fail to retain it over the delay. Okay? So pre-familiarization in that way, when in the context of knowns and novels, doesn't work the same. Okay. So 18-month-olds are so attracted to novelty, they select the most novel regardless of whether they are given a mixed novel familiar trials or all novel items. 24-month-olds are still biased to novelty such that they pick the most novel for a novel name, but known words are strong enough to override when a familiar is requested. And just a small boost in familiarity can get 24-month-olds to retain. So you could have a kind of simple picture where knowledge is increasing enough to override novelty attraction. And if you've got enough knowledge laid down, if that lexical knowledge is strong enough, those representations are strong, you can form a robust mapping that you can retain. That would then be a kind of gradual shift from something like an N3C to mutual exclusivity. Okay? But final data is going to complicate that picture a little bit as well. So in Sarah's final dissertation study, she did a reference selection and retention task, but she manipulated the strength of the known items. Okay? So she taught some novel names prior to the main test, and then she did a test to make sure they learned the ones she just taught them, and then she did the reference selection. So now we're going to have a couple different kinds of trials. We're going to have well-known trials where we're pitting the dog and the shoe against the yak. And we're going to have these weakly known where we've presented these ones. We don't call them Whisk and Slinky. Some of these are too hard for the young kids. So we just go Blicket and Toma, perhaps, and a super kind of novel object. We're going to have a series of these. We're going to ask sometimes for the known object on each of these kind of trials and sometimes for the novel. We do a within subject design in terms of these, in terms of these two kinds of trials so we can look at how they do. And we have 18 and 24-month-olds. These are the data from the 18-month-olds. And what you can see here is that on the strong trials, they do good in the warm-up. They still show that bias to go with the most novel thing, right? They do good, however, on these novel reference selection trials, no matter if it's a strong or weak. And in the cases where they get the yak here, they retain that mapping over a delay. Okay, so when the competitors are not very strong, they're able to retain that mapping. 24-month-olds show something similar but not quite the same. They show strong warm-up. Now they're showing a problem where they're going with the most novel things. The familiarity here causes them a little bit of trouble. Okay, novel reference selection, they do a great job. If they do select the novel object in this case, they do show some evidence of retention. As strong as what 18-month-olds show. Okay? So it's not simply that a stronger representation of known words can boost performance. Okay? There's this dynamic balance between novelty and knowledge that's really determining when you learn a word. Okay? I feel like, oh no, okay. So together, these data argue against accounts that suggest learning in the reference selection and retention task is based solely on representative lexical knowledge. Novelty often drives reference selection performance, but novelty is not producing retention. So I think it's this dynamic balance between attraction to novelty and accumulating lexical knowledge that determines reference selection and retention. And that's where we start to move to some different ways of looking at this. I think both lines of work demonstrate the role of systems for perception, action, attention, and memory in early word learning. We have to be able to incorporate all these interacting processes in even these simple kind of tasks. It's not single word learning constraints, and I don't even think it's a linear weighting of multiple constraints coming together. Okay? It's a balance that's shifting depending on what the child's bringing to the task, what you're presenting to them, and how you might manipulate that situation. Okay? I don't think the multiple recurrent interactions with the system's changing itself, and therefore I think we need a dynamical theory of how these subsystems are working together to help create change over timescales of behavior, learning, and development. And that's going to be this next part. We're looking at an expanded model of early word learning that incorporates the developmental dynamics of visual exploration. So processes that we know are based on novelty. And then I'm going to show you some data we're doing, studies we're doing now, or getting online to look at developmental changes and how space is used to bind names to reference. Okay, so what I have is a new model that brings together a theory of how children bind names to reference with a theory of autonomous visual exploration. Okay? This incorporates systems for perception, action, attention, working memory, and longer-term memory. So it has components, or it can handle processes of novelty, binding of object features together, binding of names to object features, and building a vocabulary over time. This is the word object model that I showed you before. I've kind of reoriented it. So the features are now on this way, and your words are here, and space is here. Sorry for the translation problem, but this is the way it fits together. We've also added some one-dimensional fields here that are dealing with attention to this scene of objects here, and working memory, and then controlling how attention is dynamically allocated to those things. This is all coded in terms of allocentric space. To this model, so this model, some other work I did in the last grant period with this model, shows that it shows comprehension versus production differences, just like young children building an early vocabulary. It also shows development of shape bias and other word learning biases based on the accumulating vocabulary. Differences depending on the specific stimuli you show, or if you do a forced choice versus a yes-no task with some of these generalization things. Vocabulary acceleration that we've seen in some of my mini longitudinal studies, and differences in the biases that develop depending on what kind of categories you show them. Okay? To this, oh, and those are our sites. Okay. To this, what we're going to do is add a model of visual exploration in space. This is work that my former postdoc, Sammy Peroni, did with John Spencer. It's a model that was developed to deal with infant visual exploration. So preferential looking and habituation tasks, where these are our measures of what children can do. This model autonomously explores a visual scene, builds up representations and working memory of that scene, and then releases fixation to look around at different aspects. So this model then can capture patterns of habituation and dishabituation and various kinds of tasks, single presentation, multi-presentation. It makes predictions about developmental change depending on things like the strength of the working memory and how that influences release of fixation. And they've also used it to look at individual differences, as I kind of mentioned already, by manipulating specifics of the parameters, or looking at cases where, for instance, premature infants show differential dynamics in their early visual exploration, and they've captured some of those kind of data as well. Okay? So a very nice model of visual exploration. So then what we do is we kind of combine these two things together to a beast of a model. Our word object learning via visual exploration model. This is in retinotopic space, and so basically you're getting information about objects in terms of their shape and their color. You could have other feature dimensions, and we do that in some cases. These fields here control attention to the retinal locations, and then this is an addition of return field that makes sure you're not always looking at the same space. This then takes information, forms working memories, allocates attention based on the relationship between these two fields, and then can put in words. Up here, the big triangle is helping us to make the transformation between space encoded in terms of retinotopic coordinates, right, and allocentric coordinates of behavior. Okay? And that's based on some other work by colleagues in Germany who have kind of helped us map out those transformations. Okay, so it's a big model, but it does make predictions about that you should see some changes. That's the basis of the new grant. One thing in particular that we're interested, well, there's a few things that we're interested. One thing it's going to let us do is move down in our studies to some earlier age ranges and some of the cross-situational word learning work that's been done in a number of different laboratories. There's a lot of controversy. We know there are developmental changes in novelty, and those influence autonomous visual exploration in a task with multiple objects and words, like cross-situational word learning. Our model can actually capture those data. There's no model out there that integrates across the word learning and the visual attention component. And it makes predictions about how we should be able to get children to learn better in that particular kind of task. So Smith and Hughes data, we've captured it. The reference selection and retention task, this one suggests that consistent spatial locations in a reference selection task might help children retain novel word-object mapping. So we haven't actually imported that component into that task with multiples. But if we do a task where you're keeping space consistent, and it's a good cue to what you had seen there when you do that retention task, it should help them to show better retention. So we're testing that. And we also know that there are developmental changes in the period that we're interested in between 18 and 30 months in children's reference frames and how they encode spatial information. Okay? So Nora Newcomb and colleagues, Janelle and Huttenlocker, have shown that sometime around 22 to 24 months of age, although there's good variability, right, that there are shifts from egocentric coding in terms of your right-left position into allocentric coding in terms of landmarks such as the screen or the door in a room. And that should mean that we should see these changes. So what we're actually doing is our word binding task, where they get familiarized with an object on one side or the other side, and then when we do the naming event, we move them to the other side of the table, right? Then when you point and name, the younger children should encode that name based on what was on their right-hand side because you're pointing, or left-hand side because you're pointing to that. Versus older children, if they're encoding it in terms of those landmarks, they should show the actual opposite encoding. Okay? And so we're testing those data. Okay, so conclusions. What I've argued for is a complex, multi-component dynamic system that supports early reference selection and retention. It's got processes of perception, action, attention, and memory. They're mutually interactive, and they're influencing each other and changing over the course of development. So we have to be able to capture all those things in our model. This is one reason why I do models, because I've got to lay down a lot of these processes and be very specific about how they're interacting. Understanding how children use their represented knowledge and developmental change in that knowledge, those two questions I started with, I think requires moving to theories that integrate across these kinds of processes and areas and across timescales. So thanks to a bunch of collaborators, graduate students who helped with all this, collaborators on a lot of that work, my funding sources, and thank you for your attention.
It seems that in most of your situations, maybe all of them, there's another human besides the child that's doing something.
Yeah.
Or it's the mother doing something, or the experiment doing something. While you're bringing in perception, cognition, et cetera, you may as well bring in social psychology too, and attempt to model the behavior of...
It's not enough?
Well, it's almost enough. But what you've done is you've compressed the person into words.
Yes, I have. Right. Yeah, and I have an explicit component. Now, I'm not going to. I have an explicit component in my research program where I am particularly interested in how far I can get with just those kind of processes alone, without having to add my understanding of what you're thinking on top of that. Okay, as a child learning. It's not to say that I don't think those things are important, right? Because children learn words from other people, right? And they're interacting, and you're absolutely right that in every single one of my tasks, somebody's there doing something, even if I'm trying to make sure the experimenters are doing very little, right? And so adding those things in are component. What I'm interested in, like with the space binding work, is I do think it suggests that part of what might be doing some of that work for the child and the parent is the fact that they're sharing this space. And that can help to organize. It organizes your attention. It organizes my attention. And if those systems work in a similar way, I should be able to map them together, right, and do that. I won't go, because I do think there's a lot to explore just with the dynamics of this particular model. I don't know that I'll go so far as to decompress the person from words yet. Okay, I haven't even decompressed words into their relationships to each other, right? But I'll tell you that in some of the work that Sammy and John did with the visual exploration model, they actually have a version of that model where they actually take two of them and they put them they expose them to the exact same visual input, okay, except the child model gets the mom model as input besides whatever the visual, like stars or whatever objects are being presented. And then the mom gets the objects and the child, okay? And what you can do is you can see then that as those things are building memories, if you bias the mom model so that it will look a little bit longer at some of the objects, the baby who builds up, what happens in that model is as you build a memory for what's there, that's what releases fixation, so you can go and get other new information, okay? But if mom's attention stays on that object a little bit longer than what this baby's attention will, they may look away, but they're more likely to come back longer than they would have, and they build up stronger, more robust working memories, okay? And that was some of the preemie work, actually, right? That has serious implications for intervention. If you can set it up so moms are doing things where they're helping to sustain their child's attention. The preemies tend to flit around more, right, and don't build as strong working memories right away. If you can get them to help sustain attention over time to this object through this other input that is the person, then that might have implications for the working memories they build up and how the system acquires knowledge. So I won't promise to add that right away, but I think there are mechanisms for it.
So let me offer an incentive.
Okay.
Just think, Quine was right as far as you can, but like in your little method where you show the mother or the experimenter announcing need, that's not the way it happens.
That's not what it is.
It's
Yeah.
playing with the
Yes.
need,
Yes.
And then the comment.
Yes.
happens.
Right.
So that all zeroes in.
Yeah.
Not on this blooming, buzzing confusion of all these
No,
objects,
right.
but that object.
Yeah, and that's where I think he wasn't. I mean, I think that's where the problem is, that the field is misconstruing what the problem is, right? It's not the problem that they've got. And the other problem, part of it is that we know as adults how many of those things might take names. The child doesn't know that. They don't yet potentially know that all of those things are nameable, right? They may not even be, they segregate out objects, certainly, but they may not be segregating them out in the way that we would segregate those out, right? Now, I know there's lots of interesting work on segregating individuating objects, and they do a lot of that processing, but we still have a lot to learn in terms of, are they pulling out in that complex environment the same thing, right? And I'll just say, you know, Linda Smith's work with Chen Yu, just showing that the stuff that's presented, you put a head cam on the baby, put them in those situations, their short arms mean it's not everything out here. This thing is here because this is what they have to attend to, right? And it turns out that moms name the thing that they're looking at in that kind of situation more often, right? And of course, then there's all kinds of beautiful early social dynamic work looking at how moms follow in on the baby, right? Or the baby guides mom's attention and how they're mutually reinforcing each other to elicit certain patterns of activation. So I think there's a lot on that front end that might be supportive as well that would be cool to pull in. So yeah. Yeah.
From the child's point of view, what space is. And I have